This is section 10.1, curves defined by parametric equations. So in this section, we introduce a new variable, t, and x and y will be functions of t. And what this allows us to do is to create, to trace a parametric curve with initial point of fa, comma, ga, and terminal point fb, comma, gb. So this would be faga, this would be point fbgb, and the direction is in the direction of the arrow. So let's trace this curve here, defined by these two functions. So we need to create a table, so t, x, and y. And t can take on any values. So I'm going to choose some negative values. I'll choose -2, -1, 0, 1, 2. And if you plug in these t values for the x and y functions, you're going to get the following values. You'll get -4, -1. You'll get -1, 1. You'll get 2, 3. You'll get 5, 5. And you'll get 8, 7. So let's draw the coordinate plane and plot those points. All right, so the first point is -4, -1. Next point will be -1, 1. 2, 3. 5, 5. 8, 7. And if you connect those points, you will see that you do get a line, and the direction of the curve was going in this direction. That's the direction. And now for part B, they want us to eliminate the parameter t and find a Cartesian equation of just x and y. So what we can do is we can solve for t in this equation and substitute it into that equation. So let's do that now. X equals 3t plus 2. If you solve for t, you should get t is equal to 1/3 x minus 2/3. So that is what we're going to substitute into the y equation in order to eliminate the parameter. So y is going to equal to 2 times 1/3 x minus 2/3 plus 3. If you distribute and combine like terms, you will get, I'm going to change the 3 to 9/3 just to have a common denominator. Our final answer should be y equals 2/3 x plus 5/3. And that's exactly the equation of the graph that we graphed up here. The y-intercept is 5/3, which appears to be correct. And the slope is 2/3, so up 2/3. That looks good. All right. Same thing for this next example. This time they first want us to eliminate the parameter, so they reverse the directions on us. That's okay. So let's go ahead and eliminate the parameter first. Whenever you're dealing with cosines and sines, you're going to want to use this identity. Sine squared theta plus cosine squared theta is equal to 1. So this equation, if you multiply both sides of the equation by 2, you're going to get cosine theta equals 2x. And over here, if you multiply both sides of the equation by 1/2, you're going to get sine theta equals 1/2 y. And now we can square this. If you square sine, you're going to get y squared over 4 plus cosine squared is going to be 4x squared equals 1. Okay. This can be rewritten as x squared over 1/2 squared plus y squared over, let's see, yes, 2 squared equals 1. And that is an equation of an ellipse. So if we sketch that ellipse, going to look something like this. 1, 2, 1, 2, 1, 1, negative 1. Okay, so our intercepts are going to be in the x direction. The x-intercepts are going to be 1/2. That's why I wrote it in this form. This tells you your x-intercepts plus minus 1/2. So that would be plus minus 1/2. And this would be your y-intercept plus minus 2. And so the graph would look like an ellipse. But they give us a certain domain. They want us to go from 0 to pi. So if you plug in 0, that's your initial point, into this in for theta. So if you plug in 0 for theta, you're going to get cosine of 0, which is 1. 1 times a half is 1. 1/2, sorry. So this is your initial point. Initial point. Oh yeah, you also plug in 0 for this equation. That sine of 0 is 0, so that's why this is the initial point. And if you plug in pi over 2, you're going to get this point up here, pi over 2. The cosine of pi over 2 is 0, and sine of pi over 2 is 1. 1 times 2 is 2, so that would correspond to that point. And if you plug in pi in for theta, you're going to get cosine of pi, which is negative 1, which is negative 1/2 for the x-coordinate. And if you plug in pi for theta here, you're going to get 0. So negative 1/2 is 0, which is this point. So our ellipse is only going to be the upper half. It's just going to be that, and the direction is going this direction. All right, and that is pretty much it. That's a Cartesian equation, and this is our sketch.